In this video, I want to talk about delta connected loads with line impedance. We're given a three-phase source, and this source can be a delta or Y configuration. It doesn't matter. What we're focusing on is the load. The load is what determines the power factor and the current draw. In this example, you can see that we're given a line voltage, delta load impedance, as well as the line impedance. We're asked to solve for the power factor, the line current, single-phase apparent power, three-phase apparent power, single-phase complex power, and three-phase complex power. Now I'm assuming you already have an understanding of complex numbers and how to convert from rectangular to polar and vice versa. What I'm focusing on is why this works on a delta load. So we can start by placing our values on the line impedance as well as the load impedance. The first thing we want to do is we want to create a single phase equivalent circuit of the three-phase delta connected load circuit. We want to convert the delta connected load to a Y connected load. As you may remember, ZY is equal to Z delta divided by 3. So we take our Z delta, which is the quantity of 110 plus J160 divided by 3, and that gives us a ZY of 64.72 at an angle of 55.49. Now let's solve for Z total. So Z total is equal to the Z line plus ZY. So that gives us a quantity 2 plus J30 plus 64.72 at an angle of 55.49. So our Z total is 91.86 at an angle of 65.10 degrees. So now that we have our Z total, we can focus on our phase voltage. So to find the phase voltage, we're going to be using phase voltage is equal to the line-to-line voltage over the square root of 3 at an angle of theta line-to-line minus 30. So the phase voltage is equal to 4160 over the square root of 3 at an angle of 30 minus 30. This gives us a phase voltage of 2402 at an angle of 0. Next, we're going to focus on the current. Now for the single phase equivalent circuit, the line current is equal to the phase current. And this is where the changing from a Z delta to a ZY comes into effect. So let's solve for the current. So the formula for the current is V phase over Z total. So we have I is equal to 2402 at an angle of 0 over 91.86 at an angle of 65.10. This gives us a current of 26.15 at an angle of negative 65.10. So you may be wondering, well, how does I phase equal I line on a delta load when we know that delta current I phase is equal to I line over the square root of 3? This is where the change from delta impedance to a Y impedance comes into play. So now that we have Z total, V phase, and the current, we can solve the following. Let's start with the power factor. So the load itself is going to determine the power factor. The power factor is equal to cosine theta. Now theta is equal to theta S and is also equal to theta ZT. So theta is equal to 65.10. So the power factor is equal to cosine 65.10, or power factor is equal to 0.42. So now we're going to move on to solving single phase apparent power. So single phase apparent power is V squared over Z, or I squared times ZT. So the apparent power single phase is 2402 over 91.86 at an angle of 65.10 degrees. This gives us the apparent power is equal to 62.808 kVA. Solving apparent power single phase using the I squared Z method, we have apparent power is equal to 26.15 squared times 91.86. This gives us a single phase apparent power of the same, 62.815 kVA. Now let's move on to solving apparent power for three-phase. So one method for solving for the three-phase apparent power is relatively easy, 3 times the apparent power of the single phase. This gives us a three-phase apparent power of 188.424 kVA. Now the second method for finding the three-phase apparent power is equal to the square root of the line voltage times the line current. So the three-phase apparent power is the square root times 4160 times 26.15 amps. This gives us a three-phase apparent power of 188.42 kVA. Now moving on to the single-phase complex power. So the single-phase complex power is equal to the complex phase voltage times the complex I conjugate. The single-phase complex power is equal to 2402 at an angle of 0 times 26.15 at an angle of 65.1. So this gives us a complex power of 62.812 kVA at an angle of 65.1. The three-phase complex power is equal to 3 times the single-phase complex power. So the three-phase complex power is equal to 3 times 62812 at an angle of 65.1 degrees. This gives us 188.436 kVA at an angle of 65.1 degrees. So the reason why I wanted to make this video is to show how changing the delta load to a Y equivalent load gives us a current that simplifies the power analysis of a delta connected load with minimal information given. I hope this helped. Keep going. You got this.